Hi, everybody. This lecture concerns chapter 24 of the E textbook about electric potential or voltage. So those two terms are kind of used interchangeably, voltage, electric potential, and voltage is related to the potential energy, as we'll see here in a minute. The unit of this quantity is volts. So you're probably pretty familiar, right, with the light bulb or electric outlets having 120 volts or your battery being a 9-volt battery. So hopefully in this chapter we'll kind of learn more about what that means. So first of all, though, we have to define what we mean by electric potential or voltage. And it's related to potential energy, which in turn is related to work. So if you recall, right, work is defined to be basically the force times the distance. Now, if you have a variable force, it's the integral of the force over the distance that that force is pushing something. In a case where you have a three-dimensional movement, you have to take the force integrated over the path. This sometimes is called a line integral, but we'll talk about that maybe in another lecture. Just remember, work is basically force times distance. Now, from the work, we define the potential energy due to a particular force, such that the change in the potential energy is the negative of the work done, right? So negative W equals potential final minus potential energy initial. And this happens just because when we calculate the work according to this integral, for example, for a spring, we get that kind of formula, right? Work is negative some quantity minus another quantity. In the case of a spring, it's 1/2 kx squared. We call that 1/2 kx squared the potential energy due to the spring. So now that we've kind of reviewed just real briefly potential energy, let's define what we mean by electric potential. I'm going to use V for that. As we'll see, it really is a change in this quantity that really matters, but we'll end up being able to define a V, an electric potential, or sometimes people just call it voltage. Now it works very simply, the relation between voltage and potential energy. The difference in the voltage is equal to the difference in the potential energy over the charge. All right, so when I'm talking about electricity, I'm talking about 2 points in space, maybe here and here. And I talk about the electric potential difference between those. That is the delta V. So sometimes you'll also hear the term potential difference. They mean the difference in the V quantity, the potential or the voltage across 2 points, right? So usually when people say voltage, they're saying the delta V between these 2 points. And it's related to the potential energy between those 2 points divided by the test charge. So the charge that might move between those 2 points. The units of voltage or electric potential are joules per coulomb, right? Energy is joules, charge is coulombs, and we call this quantity the volt. So 1 volt is equal to 1 joule per coulomb. Or you could write it as the potential energy is equal to the charge times the voltage. Now actually, this is a more general type of expression. If I know my voltage between 2 points and electric charge moves between those 2 points, what is the amount of energy that they have gained or lost? Well, you get it just by taking the charge times the voltage. As a simple example, think about a light bulb that's connected to a 120 volt outlet. If you have 50 coulombs of charge flowing through the light bulb, right, and through the wires of the light bulb and creating light, well, how much energy is used during that process? Well, to get the energy, you just take the charge times the voltage. 50 coulombs times 120 volts, 6,000 joules. Now the power would be related to the amount of time that that charge passed through the light bulb, right? Power is energy over time. So let's say it took 60 seconds for that charge to pass through. Well, the power would equal energy over time, or 100 watts, if I took 6,000 joules divided by 60 seconds. So again, voltage is related to energy and power. It's an energy type of quantity. Now, what's the reason that we define this? Well, the real reason is because we want to talk about a quantity that doesn't depend on the charge, the test charge, right? So if I plug in my toaster into the 120 volts, it's still 120 volts. But the amount of energy that the toaster uses depends on how much charge goes through it and how long it's plugged in for, right? How much total charge gets through that toaster. So different devices will use up different amounts of energy, depending on whether or not more charge is going through them. But they are still connected to the same voltage, 120 volts. So that's what really one of the reasons we define voltage. We want to talk about a quantity that doesn't depend on the charge or the test charge that's going in there. As an example of a particular situation where we can calculate voltage or talk about voltage, let's look at the capacitor, right? And the capacitor, again, is just two plates, a positive and a negative. We've talked before that the electric field is uniform in between there. In our case, let's say that the electric field is 100 newtons per coulomb, and the distance between the plates is 10 centimeters or 0.1 meters. So the voltage, we can talk about the electric field, but what is the voltage between these two plates? And so what I mean is if I took a voltmeter, a device that measures voltage, and put one probe on the positive plate and one on the negative, what would the delta V be that I got there? All right, well, it's related to the energy divided by the charge. That's the definition. Now, energy, delta U, change of potential, is negative work over the charge. Now, work is force times distance. But for electrical fields, we've talked about the force is the charge times the field. Now, notice the charge cancels out. And that's really the main point of what I was saying. This quantity voltage does not depend on the charge that's in that voltage. So when the charges cancel out, you'll get this expression. Voltage is negative the integral of the electric field across the plates. Now we'll maybe talk about this integral in more detail for other situations, but for this case, the electric field is uniform. I can pull it out. And so then what I just get is the voltage is negative E times D, just the field times the distance between the plates. So plugging that in, 100 newtons per coulomb for my field, 0.1 meters for my distance, I get negative 50 volts. Right now, voltage is kind of a little bit abstract like electric field. So what do I mean by the negative 50? We always define our quantities in electricity in terms of positive test charges. And then we just say the negative test charge does the opposite, right? So I'm talking about a positive test charge. If I put a positive test charge right here, like a proton, for example, or something, I would say it's kind of at the top of the hill, right? It's wanting to be pushed down toward the negative charges. And so I have a higher potential energy, a higher voltage over here. So the negative sign just refers to as I go along the field, my voltage is dropping, it's going down, right? I'm going from a higher voltage to a lower voltage along the field. Now for an electron, if I put a negative charge, it would go the other way. It would kind of go up the hill. It would actually go the way of increasing voltage because it's a negative charge. Right? But we typically define everything in terms of our positive test charges. So the negative sign just tells me, oh yeah, the voltage is going down if I go along the direction of the field. Now to draw, I could draw what are called equipotential lines. This drawing's not that great, but right, I have 50 volts at my positive plate. I could define 0 at my negative plate. So if I look everywhere in between, in this case, at equal spacings, I drop by the same amount of voltage, right? And this actually is really just this relation. I can rearrange this and say, oh, my electric field is the negative change in voltage over the distance, or negative delta V over delta X. Electric field is the negative kind of slope, or I guess, yeah, slope of the voltage, how fast it's changing. The faster the voltage changes, the bigger the electric field. So you go, maybe down to 37.5. Midway between, you're at 25 volts, down to 12.5, and you finally get to 0. But these lines, where those potentials are the same, 25 volts, for example, along this line are called equipotential lines. Now, the electric field is always perpendicular to those lines. Okay. So we'll talk about that more for point charges, but one last thing I want to talk about is, since voltage is related to energy, right, you'll often see or deal with conservation of energy. So let's just take a quick example. I won't really plug in numbers here, but let's say I have a positive charge up here and I've got my 50 volts between my plates. What is the potential energy of the charge? Okay. Well, at the top, the potential energy is QV, right? Whatever the charge is times the 50 volts. Now, let's say you let go of that charge. Well, what's going to happen? It's going to shoot down until it ends up with a velocity down here. It's going to accelerate, right? There's acceleration due to the field. It's going to pick up speed. It's going to pick up kinetic energy. So what happens? How can I calculate that kinetic energy? Well, from conservation of energy, I started with potential energy here, and I end up with kinetic here. So this QV will have to equal 1/2 mv squared. And again, voltage, I'm using a capital V. Velocity, I'm using a small v. So just like dropping a ball near the earth, the potential energy has turned into kinetic energy. I just have a new type of potential energy, charge times voltage. All right, so in the next lecture, we'll talk about the voltage or the electric potential due to point charges. All right, but I will stop here at this point.